Our next presenter is Prangl. He works as a systems engineer for Arista Networks. Based in Austria, he is passionate about networking and automation. Please join me in welcoming Patrick to the stage and enjoy the talk.
Thank you very much. Yeah, today I'm talking about optics, which might be a bit unusual for a network gear vendor. Why I'm talking about optics is pretty easy. Some customers approached me the last kind of 2 years with one question, and that was basically when 800G, right? And I was like, well, we will deliver 800G, of course, we will also deliver 1.6 tera, but what does it actually take to deliver kind of higher bandwidth speed or higher bandwidth products? And the second question I want to address is, you know, some kind of people of the service provider industry approached me, and they were like, you know, I'm a classical network engineer, so my basically knowledge starts, or knowledge, what I want to care about starts at the Ethernet kind of layer, and then it ends at the IP packet. I don't want to care about optical stuff. And if we go down the road of coherent optics, you basically need to develop more and more kind of optical knowledge, right, to understand those technologies and what it takes to kind of realize such transports. So I want to start by answering the first question, which is, what does it take to produce higher bandwidth product? And there are 3 things we need to kind of take care about. First thing, of course, is the transceiver itself, the pluggable, which we insert into our switch, router, or whatever you want to call it. But there are 2 other kind of pieces we need to take care, and that's, of course, the chip, the ASIC, which does the forwarding, and there is something in between the ASIC and the transceiver, which is called SerDes, serializer or deserializer, which is basically the electrical lane connecting the front-end pluggable with the chip, right? And all needs to fit together. And I want to start by giving you kind of a glimpse on kind of how those network chips have evolved. In my case, I'm talking about Broadcom ASICs because that's basically available to everyone. And if you have a look at the diagram, you see that currently we are at 50 terabit. That's what we are currently shipping. That's the capability of the total chip, which basically runs at 100G SerDes, which means the electrical interface between the chip and the front-end pluggable is based on 100G PAM4. The next kind of iteration will be a 100 tera kind of ASIC, which will be shipped this year. Sorry, the next year, 2026. It's still 25. And basically the switch or the product will ship next year, but the ASIC was already released by Broadcom. And if we have a kind of an outlook to 27, we expect a 200 terabit chip, which is insane, right? When I started basically tinkering around with the internet, still had 54K, right? And now we have 200 tera in one chip, right? Now think about a product who has 10 chips, right? It's 200 by 10. And if we look at 100 and 200 tera, right, we operate at 200G PAM4, which means the electrical lane doubled, right? And why this is important, I will basically show you later. If we go on having a look on the chips, Jericho 2 is basically what Broadcom was now shipping for years. Jericho 3 is what Broadcom is shipping since this year. There was kind of a derivative of Jericho 3, which was for AI use cases, so forget kind of that stuff, because for most of the people in that room, it's about kind of the interconnection world, and that's basically a full-scale Jericho 3. What I want to mention is just people are confused because there is like Qumran and Jericho, and what's the difference? It's basically the same stuff. Right? A Qumran is just a Jericho without the fabric interfaces, which means if I have a Qumran, I can only have a single chip switch or router, If I need to have multiple chips, I need those fabric interfaces on the ASIC, and then I need to have a full-scale ASIC, like the full-scale Jericho. Also, what is pretty interesting, all of those chips starting with J2C+, have built-in crypto capabilities. Basically, you can run MACsec, IPsec, whatever, in the chip itself, and don't have to put kind of some other crypto chips on the box. Nevertheless, if we basically have a look at the evolution, when we started with J+ in 2016, we were talking about, I don't know, like something 2.5 G. If we now have a look at Jericho 3, what is basically interesting, while the aggregate bandwidth was increasing, the power per bit was decreasing. So why is this important? Especially when we run optics and we have like high density deployments. It does matter because if we have a look at ZR plus optics later on, especially the 800G and 1.6 tera optics, they take up to 30 watts per optic, right? And then, of course, it doesn't matter if I have 2 watts per optic less or more, and if the chip does take less kind of power or not. Why? That's the kind of processing form factor, right? So if we have a look at Jericho 3, we are producing it in 5 nanometers, which explains why it has overall less power consumption per bit, because we have a better or a smaller processing node. Again, it's based on 100G SerDes, which makes it optimal for 800G front panel ports. And now basically I was always talking about 800G, 1.6 tera. So what's the status, right? So I think currently every vendor is shipping 400G for sure since I don't want to say since ages, but since quite a while. So what's the status? So initially there was a draft for 800G and 1.6 tera. It was basically, it should be one standard. Well, the problem is it took so long to agree, especially on the 1.6 tera stuff, that the consortium decided there is a pre-standard, which was the ETCR, which you see in the middle of the slide. And currently all the products, the initial products were based on that kind of pre-standard. And now we have 802.3 DF, which was reduced only to 800G8. Basically, it's 800G by using 8 times 100G lanes. And they decoupled all the other kind of stuff from this standard. Why? Basically, to ship 800G earlier, right? And not to wait for 1.6 tera. So since February 24, we have that kind of 800G standard. And the pre-standard and the standard are basically interoperable or compatible, right? It's basically the same. It's just now in a standard. And 800G is basically shipped on Tomahawk 5 and Jericho 3 from an ASIC perspective, right? If we now have an outlook to 1.6 tera, which is then based on 200G SerDes, so 200G electrical lanes, the DF, again, that's the 800G standard, and the DJ standard, which should come maybe, let's say maybe in the third quarter of next year, which does, of course, include 1.6 tera, and different other kind of standards on 200G, 400G, and 800G, which are already available, but those new kind of standards implemented on 200G electrical lanes. So 800G-4 would mean, compared to now, we have 800G-8, it's 8 times 100. In the future, we can have 4 times 200 to achieve 800G gig. Why do we do that? Save power, right? That's basically all about that. So basically to give you a glimpse on what that actually means, because I'm always talking about those magical electrical lanes, right? So what it means is, of course, from your perspective, it's the left side, right? You have the chip, and the chip has electrical interfaces, kind of pins, where we can connect stuff, right? And that kind of stuff is SerDes, that's the electrical lane, which we connect to the transceiver. If that kind of speed is not matching to what we need on the transceiver side, we need something called gearboxes. That's like a speed switch or speed change kind of device. So basically, when we have a device which is running 50G electrical lanes and we want to have, for example, 400G, then we need a gearbox to translate between 50 and 100, or if we have 100G SerDes and we want to have 10 or 25G speeds, then we need to switch those speeds on a gearbox. It's just like an electrical piece which is converting those speeds. So that's basically on SerDes. In sake of time, I just want to give you an outlook on what does it mean to transition to 200G SerDes. So everyone should basically understand that, of course, you have interference and you have other phenomena on this electrical channel because it's basically high bandwidth, right? So it's not that easy to just say, okay, I'm now running 100G SerDes and next week I'm doing 200G because I just want to do 200G. There are some kind of things which we need to consider from an electrical engineering perspective. And that kind of SerDes interface, it does support like all the stuff you know, duct cables, AOC cables, LR, SR, whatever it means, because that's on the optical side and not the electrical side, right? If we're doubling that kind of density, right, we're reducing cost per bit and also power per bit, right? So we don't do that just for fun because someone is bored, right? We do it really to save costs at the end of the day. If we have a look at 1.6 tera, all the other kind of different standards you're knowing will be available, be it like SEDA, SEDA+, DR, FR, SR, right? All of the options you have today will be available. And all the new kind of ASICs, all the new chips will transition to that 200G electrical interfaces in future to make that kind of jump to 1.6 tera. If we have an outlook, and that's like a report from Del Oro, which is like an analyst group, they basically expect that in 2026, 800G will be peaking. I think it's true, but you have to consider it does include all the hyperscalers, all the AI networking, et cetera, et cetera. On the interconnection side, I think 800G won't peak, but it will develop, right? It will slowly start. And we expect that by end of 26, 27, 1.6 tera will start taking over, all right? So what I also want to discuss today is basically what kind of different optics do we have, right? What kind of options do we have? At the very bottom, you see the full retimed optics, which is the optic you basically know by today. We have a DSP chip, which is doing encoding, but it takes power, right? And if we think now about AI networking, that has like an insane scale, which means you basically need to run a nuclear power plant to run your AI cluster. And that's in fact also what the hyperscalers are doing. So what we basically came up with, and I don't speak of Arista, it's basically the industry, we came up with something called linear pluggable optics, or LPO, which you see on the very top. Basically what we do is we take that DSP out of the optic, and that function will be put into the ASIC. So why are we doing that? We are cutting power consumption by 50%. If a full retimed optic does need 20 watts, the LPO version of it would need 10 watts, right? And I think that's basically an insane power saving. One thing you need to consider, the ASIC and the SerDes interfaces need to support LPO optics. Not every chip will support it. Jericho 3 and Tomahawk 5 are already supporting it. Take that into consideration. So what does it mean? You have the DSP, it's marked in red. I hope you can see it. And that digital kind of processing unit is removed. There is just like the laser, and the DSP function is basically pushed back into the chip of the networking equipment. If we have a look on some statistics, and I have, I won't say I've stolen it, but I have borrowed it from Andy Berchtesgaden. What does it mean? That's basically what we see in the lab, right? If we take 800G DR8, which is produced on 5 nanometers. The normal optic, kind of the fully retimed optic with the DSP, takes 15 watts, 7.5 on the LPO version. There is the LRO, which I haven't talked about. It's like a kind of half retimed optic. It does only retime in one direction. That would also save some costs. But we currently don't see a value in them, because with LPO you cut it by 50%, right? And the complexity difference between LPO and LRO is not basically worth it. But just to mention it, there is also like a half retime optic. If we look now on 1.6 tera, and yes, we have it already in lab systems, 1.6 tera, manufactured on 3 nanometer, does take about 25 watts, believe it or not, per optic, right? If we go into LPO, and there is also another concept I will talk about later, which is co-packaged, which basically is the same principle from the transceiver perspective, have only 10 watts. So we consistently cut it by 50%, right? If you have one optic, you might now say, is it really that kind of much of a power saving? If you have 1,000 optics and you have half of the power consumption, that's like a big number, right? I'm not insane. I have put 100, 200, 300%. It's not about the percentage. It just should give you a scale, right, to kind of figure out where are the difference. So kind of a system level perspective, which means the whole box, including all the optics. You can see on the right side, on Tomahawk 6, with LPO optics, you have basically 1/3 less of power consumptions, including all the fans, the power supplies, which are basically the same for the box, right? But just by cutting the optics to LPO. So what does it actually mean? LPO, linearly pluggable, it means I have the same transceiver just without the DSP, but for you it just feels like a normal transceiver. You stick it in, you push it out, you can do basically what you can do with a fully retimed optic. And then there are other concepts to save power. There is like a near packaged optics, which means the transceiver is not on the board, which would be co-packaged. That's the board where the ASIC sits. So the transceiver is basically glued onto the board. That's co-packaged. And near packaged is somewhere in between. It's not on the front panel, but it's also not on the chip, on the board where the chip resides. It's kind of halfway in between. Some other kind of vendors talk about co-packaged a lot, right? And they can save power and so on. And that's true, they can save power, but we can save the same amount of power with LPO. What is the difference? Difference is pretty simple. It's just the maintainability, right? If I have a co-packaged system and the transceiver is on the board, when one transceiver fails, what does it mean? I need to change the whole box. Right? With LPO optics, I just changed the transceiver. Right? That's basically the difference. We have kind of both in labs. Both are working. Again, it's just a matter of maintainability. So to speed up stuff, when we have a deeper look at the LPO results, as I said, by 50%, that's the amount of power we cut. There are some specifics. I think in sake of time, I'm not going to bore you with all the details about the bit errors and all the testing we have. The main message is we can deliver also 200G PAM4-based electrical channels for LPO systems. So it's good and clean enough to deliver LPO optics, right? So the electrical channel is clean enough. First results look really promising that we also can deliver LPO at higher speeds. That's basically the main message. That's basically what I told you before. Maintainability is a key difference. Like if you have to change a transceiver, right? In most of the cases, it's not the switch which is faulty. It's also not the transceiver which might be faulty. It's more or less that we have those kind of soft failures, which is the optical unit on the transceiver is dirty, right? And that's some kind of dust particles or whatever. You can't just easily clean them with some kind of cleaning tool. And that's what we analyze in our kind of basically RMAs, where the most faults are residing, right? So advantages of LPO systems. is clearly maintainability, right? It cuts power by half, but I can still easily replace the optic by just putting it out and replacing it with a new one. Other than that, there is no difference. In terms of power saving, co-packaged, LPO, LRO, it's basically all the same. The difference is just like where the transceiver resides and how easily I can change it, right? If we talk about ZA, ZA+, kind of coherent optics, I skipped that kind of slide. What I want to show you is basically the outlook. 400G ZA+ is currently deployed. All right, I'm talking regularly to customers who are deploying 400G ZA+. So what's coming up? Basically, surprise, 800G ZA+, 1.6 tera ZA+. Right? Of course, what is the difference? Now we have 75 to 100 gigahertz on the grid. With 400G, it will be 100 to 150, and then it will be to 300 gigahertz from a spacing perspective. And yes, you're reading correct. A normal kind of fully retimed optic will take up to 40 watts on 1.6 tera. So it's getting hot. And also expensive from a power budget perspective, right? So to conclude the talk, I just wanted to give you a brief outlook on what the industry does think about, right? And I think it's pretty insane because I haven't thought about it. Of course, we're thinking about how to save power, right? Especially in data center networks, in AI kind of classes where you have thousands of optics. 50% saving is a lot, right? We also think about how can we optimize the optical part, right? Kind of stuff like micro LEDs or terahertz guided waves for like a short kind of interconnect, which is like 10 to 20 meters. Might not be the use case for service providers, but again, in the data center or in the AI landscape, that's often enough. Of course, a bit of AI is everywhere, so also AI-driven kind of network automation, also on the optical side. And what I pretty like is like the pre-last point is like hollow core fiber. So if you think about AI classes and all of that kind of stuff which is coming up, we care about latency, right? So we found that in our products, we can't really decrease latency more and more. So what people started to think about is, if light has to travel through like a silicon, which we have in our fibers, right? It takes more time than when it travels just in air, right? So hollow core fiber means actually it's a kind of empty core fiber where there is just some form of air, right? Of course, it's not the stuff we breathe, but think about that. We just remove the silicon from the fiber to reduce latency, not by half, but by 0.6. And I think there are some trends which are pretty interesting. And of course, for interconnecting kind of data centers and kind of stuff, we look at 1.6 tera. If you talk to NDP, he's already talking about 3.2 tera. I think it will take some years until we are at 3.2 tera. But 1.6 is reality, right? So the first lab systems are already running. It looks pretty promising, right? So remember, LPO is something you can also think about in interconnection, right? Because what cares for interconnection is the optical side. Is it LR, LR4, or whatever it needs to match with the partner or other providers or customers? That has nothing to do with the LPO, because that's just how the switch is connected or the ASIC is connected to the transceiver. So also service providers can basically take advantage of that kind of technology because it doesn't affect the optical side, right? Basically, that's it. That was like a brief overview. I don't know. Are there any questions?
Yeah, thank you, Patrick, for these insights. I guess we will have lots of fun with optics in future, and the number of options to choose from will increase even more. We have some time for questions. Please remember to state your name and your affiliation before asking your questions. We will also relay some questions from venueless if time permits. There is a question here.
Yes. So, hi, Q. Max Planck Institute. Is this mic up? Q. Max Planck Institute for Informatics. So I wanted to ask about CPO and LPO optics, and just check that I'm understanding it correctly. So CPO optics basically everything is in the switch.
Yeah.
So then if one wanted to change to a different frequency of light, you would have to replace the switch. Is that correct?
Yeah, it's correct.
And okay, so then LPO optics, you would still have all the flexibility that you have with the current optics of it doesn't really matter what kind of light you need. Like the DSP doesn't care what light it's driving.
Yeah,
as long
exactly.
as the laser is correct.
Exactly.
Okay.
So with co-packaged, there are some kind of modular things, but it's not that easy that you just plug out the transceiver. You need to open the box.
Because what would be really nice is just being able to plug in whatever light we need.
It's glued to the board, actually, right? And with LPO, as you said, like if you have LR, SR, whatever you have, it's still basically the transceiver which determines it.
Yeah. Okay. Thanks.
Yeah, thank you.
Hello, Max from NetPlans. Thank you for the talk. When removing the DSP from the optics, obviously this saves power, but is it really removed or just moved somewhere else? And is there any implication on power consumption of the ASIC or the line card?
Yeah, so it's not totally removed. Basically, the DSP function, right, is moved into the ASIC. So the ASIC does take over. And yes, of course, the ASIC does need more power, right? But it's not the 50% you save on the optics, right? But of course, a few watts will be then taken by the ASIC, right?
Okay, there's a question here.
Sebastian Schrader, TU Dresden. As far as I remember, LPO doesn't have the same reach, right? So there won't be any ZR plus LPO. So it's mostly for inter-data center or inter-AZ stuff, correct?
Currently, there is no ZR plus on LPO because there is
also, I think, not possible. You need
you don't have basically you don't have the capabilities in the ASIC to refresh the signal and produce it. So currently there is no ZR plus or ZR optic on LPO. It's just a regular
not even
optic.
ER or other.
We don't plan it currently because it doesn't seem to be kind of possible to build it, or in a way which makes sense to produce it.
There's a question right there at the top, and that would be then the last question for this talk.
I'll get out of the way. Hi, Remco van Mook. So you briefly, at the very end of your presentation, touched on, I think it's very, one of the more interesting parts of your presentation, which is the hollow core fiber. I've seen hollow core fiber coming in and out of existence in this industry for, I think, the last 16 years. And the last thing I know about it is essentially Microsoft buying the single company that was basically getting ready to build this in production volumes. So I'm getting the very distinct impression that that hollow core fiber technology is the single most NDA piece of networking equipment out there. Can you comment on this?
Well, first of all, we don't produce fibers, so no. Yeah, I mean, it's also like for the interconnection kind of community, it's also not that relevant because you don't dig like kind of out the classical fibers and replace it with hollow core fibers. There are also some interesting questions which came up about what if there is a fiber cut, right? Because currently we are splicing fibers. How do we splice air, right? And I think that's a fair question, and I don't have the answer for that. But yes, hollow core fiber, it's coming up, right? But I see it more recently only in like AI kind of networks, so very specific use cases where they use it. And there is anyway like not much choice on the GPU side of things. So yeah. But it's a fair point, and I don't have like a very detailed answer, unfortunately. But I don't see it coming up in the interconnection industry that far.
If you ever considered submitting a presentation again, I would very much encourage you to do one about hollow core fiber. I'd be very interested.
Okay, I will consider it.
Next year then.
Thank you.
Thank you very much, Patrick. That's a wrap for this presentation.